Cheltsov from Edinburgh to have to visit us and speak on case stability of Fano threefolds.
Yeah. Okay, thank you very much, Ilya. So basically my talk, wait, Ilya, as a host, you should mute everyone else. Yeah, otherwise it's going to be noisy. Okay.
Lina, you are the host, so you can mute everyone.
Okay. Except me. Hello, can you hear me? Okay, I think everyone.
We can hear you.
We're good.
Good. Okay. So I see Chin Yang is here. So my talk is basically a prequel of talk of Chin Yang and our Edge seminar, and also it's inspired by the conference organized by Chin Yang in January. But I will start slowly. So so it's sort of algebraic geometry colloquium style talk, first part, a little bit. So let me remind you that if you have a projective normal complex variety of dimension n, yeah, so it's called Fano if anti-canonical divisor is Q Cartesian ample. So here we don't assume any condition on singularities, so singularities can be anything, yeah, so far. And the number minus k to the n, I mean, it's the top power of anti-canonical divisor, it's called degree of Fano variety. Yeah, and top main example of Fano varieties are projective space, weighted projective space, Grassmannians, hypersurfaces of low degree. This is all examples of Fano varieties. Okay, up to basically this is if you give a colloquium talk on Fano varieties, this is how you should start. So more or less, yeah. Okay, so these are Fanos. I hope everyone happy with this definition, yeah. So in dimension 2, traditionally, so by the way, if you go back a little bit, Fano variety. Why Fano variety is called Fano varieties? Because Fano studied varieties similar to what we know as Fano varieties. He called them varieties with like termination of adjunctions condition. So, and later Iskovsky, who gave original definition of Fano variety, this definition, he called them Fano varieties. But before Fano varieties studied Fano varieties, Marquis, Pasquale, Del Pezzo studied surfaces which later were called Del Pezzo surfaces, and Del Pezzo gave them slightly different definition, but it's the same as basically what is here. So Del Pezzo surfaces are two-dimensional Fano varieties. It's just tradition to call two-dimensional Fano varieties Del Pezzo surfaces. Okay, so if we consider only smooth Del Pezzo surfaces, we have very clear classification, very nice one, short. We have 10 families. So we have 4 toric ones, these ones, P2, P1 cross P1, and P2 blown up in 1 point, which is called Hirzebruch surface, and P2 blown up in 2 points, and P2 blown up in 3 points, which is easier to consider as a divisor in P1 cross P1 by the 3 degree 1, 1, 1. Then we have a non-toric one, the first non-toric example, but it's unique. So it's a blow up of P2 in 4 points. Sometimes it's called quintic Del Pezzo surface, very nice example. Can be also obtained in sections of Grassmannian. And we have 4 complete intersections in weighted projective spaces. So we have sextic in P1, 1, 2, 3, quartic in P1, 1, 1, 2. Sometimes it's called double plane, yeah, and quartic double plane. And then you have the most classical example, cubic surface in P3, and complete intersection of 2 quadrics in P4. All of these varieties are important. Del Pezzo surfaces, complete classification. So the small index is a degree. So one can consider what's called Calabi problem for Fano varieties. So it's existence of Kähler-Einstein metric on Fano varieties. Notion of Kähler-Einstein metric only makes sense for Fano varieties, for Calabi-Yau varieties, and for varieties of general type with ample anti-canonical divisor. So for for positive canonical divisor for Calabi-Yau, Calabi problem has positive solution. There's always exists Keller-Einstein metric. But for Fano, we have abstractions. And the first abstractions is basically given by Matsushima. This is if Fano variety has if Fano smooth Fano variety, complex Fano variety has a Keller-Einstein metric, its automorphism group must be reductive. And this is the first two examples when automorphism group is not reductive. So if you take a P2 blown up in one point, it's this is the group which you're gonna have. And if you blow up 2 points, this is a group, basically just product of two barrel and permutation. And here you have 2 copies of unipotent additive group and PGL2. So these two groups are not reductive, and this implies by Matsushima abstraction that these two surfaces does not have Keller-Einstein metric. And the classical result of Tian, which goes back to 90s, says that all other smooth del Petzer surfaces are Keller-Einstein. Okay, so basically Tian stated the theorem in his paper in Inventiones is like smooth del Petzer surfaces has Keller-Einstein metric if and only if automorphism group is reductive. But proof was more or less case by case. He went through different families, which I described on the previous slide, and just proved that in each case metric exists. Okay, so this eventually and other results led to this famous conjecture, Yau-Tian-Donaldson conjecture, which basically says that if you have smooth complex Fano variety, it's Keller-Einstein if and only if it's K-polystable. Okay, so K-polystability is technical notion, and I decided in this talk do not give a definition, because this notion, first of all, this notion evolved over the last 20 years. It's changed a bit, and it was simplified, and eventually we have a very nice criterion for being K-stable or K-polystable. So in some sense, it's better use this criterion than definition, at least in the talk. So anyway, so we have this conjecture, and this conjecture was proved by Chen, Donaldson, Sun, and independently by Tian, so it's true. And just to clarify the difference between K-polystability, K-stability, so if Fano variety has a finite automorphism group, which is very often, then being K-polystable is the same as K-stable. But K-polystability is K-stability plus some extra conditions coming from automorphism group, which we will see later a little bit. Yeah. So both conditions are purely algebraic, and in particular, being K-polystable implies that Fano varieties must have mild singularities. So since they're algebraic, they make sense for arbitrary Fano varieties. You can state them for Fano varieties with any singularities, not necessarily smooth. But being K-polystable implies that singularities must be mild. In particular, it means that it should have what is now called Kawamata-like terminal singularities. If you don't know what it is, it's okay. But in dimension 2, it basically means quotient. And in high dimension, it's, for example, in dimension 2, it basically means quotient. But in general, it's complicated singularities. But smooth are okay. For example, ordinary double points are fine in all dimensions. Okay, so to state what is K-stability and K-polystability, as I said, I decided not to use definition. I decided to use some criterion, recent criterion. And to do this, to use this criterion, I need to define 3 numbers, traditionally called alpha, beta, and gamma. So to define them, so we fix Fano variety with KLT singularities. Then we take some birational morphism with normal y. So this F can be identity. And then you take any prime Weil divisor in a y. So it may be F exceptional, or maybe not F exceptional, maybe it's an X. And we say that E is divisor over X. And then we define these two numbers. One number is very, very traditional for birational geometry. It's called log discrepancy. You look for the order of relative canonical divisor. So basically you pull back canonical divisor from X, subtract it from canonical divisor from Y, and then you choose the order of vanishing and add 1. This number appears everywhere in, say, minimal model program. You define singularities of varieties using this number. So for example, being KLT means that this number are always positive. So X has KLT singularities if and only if all such numbers are positive for all divisors over X. And then we can state, so again, this number has an this A of E has a local structure, local nature. But then we have this global number, tau of E. It's called pseudo-effective threshold. So you pull back anti-canonical divisor, this guy is sample, and then you start subtracting exceptional divisor until basically this divisor stops being pseudo-effective. This is a rational number. And okay. And then you use this number to compute this integral. So you have this integral from 0 to infinity, but it actually stops at pseudo-effective threshold. You take the volume of this divisor. If you don't know what volume is, it's okay. So basically, if this divisor is nav, volume is just a top self-intersection, top degree, just the degree, nth power of this divisor, where n is dimension. But if it's not nav, but still kind of big, then one option you can consider Zariski decomposition and has a volume of this nav part, or you can blow up X a little bit if you don't have Zariski decomposition such that the corresponding divisor has Zariski decomposition, and then you has a nav part, or you can define it using the asymptotic Riemann-Roch. So there's, instead of giving definition, I just will show one example in one slide later. So you have this integral. This function is nice. It's continuous, and even more than this, it's differentiable. And in every example, you can compute it. So if you fix X, if you fix Y, if you fix this map, it's possible to compute it. It's gonna take time. Sometimes it's long, but it's computable. So you have this number. Okay, and then using these two guys, we can define three numbers. One is the simplest one. It's called beta, beta of E. It's basically a difference between log discrepancy and this S. Yeah, this is the main guy in some sense. And the second is you can take a ratio. Oh, sorry. No, it's okay. So you take a ratio of A over pseudo-effective threshold. And this is known, but it's given by different definition, but this is probably the simplest definition. This is it's alpha invariant of Tian. So you take infimum of all these ratios. Yeah. And the second number introduced by Fujita and Adaka, so it's called delta invariant. So you take infimum of this ratio A over S. Yeah. So basically, if you look at this integral, you can actually see that this number delta is clearly bigger than alpha. Yeah, but we have more explicit result. Basically, because the volume is log concave, you can show that delta is bigger or equal than n plus 1 over n alpha when n is dimension, and it's less or equal than n plus 1 times alpha. Yeah. So there's three numbers. So this alpha is old. Alpha basically was defined by Tian in his paper in 1997 in Vincennes. So this is old number. These two numbers was introduced relatively recently. And delta can be defined using different way. Okay, good. So what is K-stability? Basically, before defining K-stability, there are three relevant notions: K-stability, K-polystability, K-semistability. and you have this implication. K-stability is the strongest one. It's implied K-polystability. And this one, in turn, it's implied K-semistability. And if automorphism group is finite, K-stability and K-polystability coincide. But these two guys are quite different. Yeah. Okay, so there's a theorem by Bloom, Fujita, and Xu, Chenyan, Xu, Kento, Fujita, and Bloom. Yeah, so it's basically said that you can think of the theorem as in this talk as a definition that X Fano variety is K-stable if this beta of every prime divisor over X is positive. So yeah, so this is actually, it's a criterion, it's called sometimes evaluative criterion for K-stability, but for this talk you can think of this as a definition.
Well, sorry, I think it's also proved by Chili.
Sorry, Chenyan.
Sorry, yeah, it's also proved by Chili.
Yes, I will amend this, but Chenyan, it's good. I actually copied the reference from your survey on your webpage.
Really? Okay.
Yeah. So at least I think so. At least one part of this. Okay, but okay. Let me say this. Yeah, let me say this. I may accidentally omit some names because this field is so active and so nice. So basically, I may accidentally miss some references. So okay, but I try to. Chenyan nowadays, right now, is writing a very nice survey paper about K-stability. So which basically contains everything. So when I prepare this talk, I could use this, but maybe I'm forget. But okay, let's add Chili here. I will add after the talk. Yeah, okay. And yes.
So the condition here depends on the birational map F.
No, it depends only on valuation.
Only on the evaluation. It's independent of the.
Yeah. It depends only on valuation.
Y and F, right?
Yeah, it depends on valuation. You can change different F, but it basically depends on valuation. Yeah, this is a good thing.
Okay. Thank you.
Is a good thing. Okay. Anyway, everything is good. Okay, and since Chenyan is here, so I wanted to put somewhere a nice quote from Chenyan's survey. So the K-stability is the best gift that differential geometers gave to algebraic geometers. So which is probably should be the motto of this talk. But anyway, so okay, let's continue. So we have the theorem. Think about it. So and Bloom, Fujita, Xu, Chili, and very nice theorem which you can take as definition. But of course, so it doesn't define immediately K-polystability. It gives you K-stability, K-semistability. K-polystability is a bit more subtle. I'll tell about it a bit later on the next slide. But this theorem, together with the previous slide, implies this corollary. And this corollary, it has more names because basically it was some parts of this corollary was proved earlier than the theorem. So this field is so rich, so some nice results comes after the other results. So in particular, we have this nice criterion here. X is K semi-stable if and only if delta is bigger or equal than 1. So because of this, quite often delta is called stability threshold. Then we have this condition X is K stable if delta is bigger than 1, which is very applicable. So this line is basically you can apply it and quite effective. And then you have very classical result by Tian for in smooth case. If alpha invariant bigger or equal than dimension of dimension plus 1, that X is K stable. So this is basically the Tian's.
I should say that alpha invariant was introduced by me and 10 together, not 10 only.
Wait.
This is Yao.
Oh, Professor Yao. Okay, now
alpha invariant was introduced by me and him together in the paper. And
okay.
He doing more extensively.
This is true. Okay. Okay. Okay, anyway, it's good. Yes, alpha invariant was introduced in, yes, it's correct, and the paper, I think, in 1988, in a joint paper of Professor Yao and Professor Tian, as far as I remember, about the Calabi problem for Delpezzo surfaces, the first paper. Yes, and okay, good, okay. Okay. So anyway, we have this nice corollary. We will go back to this corollary a little bit later. But anyway, let's continue. So so here, basically, we have very clear algebraic condition, computable in many cases explicitly, for K-stability. K-polystability is more subtle. So for this, we have another results which are very recent. So it's basically just some of the results appeared on the archive last week. So first of all, let me remind you that if Fano variety is K-stable, then automorphism group is finite. And if automorphism group is finite, then K-stability and K-polystability is the same, coincide. But a very recent result by Alper, Bloom, Halpern, Leister, Matsushima, it's in the smooth case, and Chinyangxiu, basically says, it's very recent, it says that if Fano variety is K-polystable, then automorphism group is reductive. And if automorphism group is reductive, and you can use the previous condition for beta invariant, but only for invariant prime divisor, which invariant with the automorphism group, and you assume it's reductive, then this implies that X is K-polystable. This is very recent, so it's basically several people proved some parts of this. It was, yeah, and the final paper about this was proved by Jiquan Zhuang, and I think it's appeared on archive like maybe I think it's last week, maybe even this week. Yeah, so basically, so this is actually, if you think about this, it's very, very applicable. So here I is deliberately put different colors. So very important word is prime. So because, for example, if you have some group, there's a lot of divisors which are G invariant. If you have some group acting on variety, a lot of divisors which are G invariant. But quite often, it's very few divisors quite few prime divisors which are G invariant. So some here, this word prime is it has to do something with connectedness. So like a Kolar-Shakurov connectedness principle. So this is actually quite powerful. So for example, just in one line, we have a corollary that smooth Delpezzo surfaces of degree 6 is K-polystable. Because smooth Delpezzo surfaces of degree 6 are toric, but its automorphism group, it's torus, two-dimensional torus extended by symmetric group of order 6. So one can check that basically there are no G-invariant prime divisors, where G is automorphism group in this case. So there's a lot of, for example, torus, you act by torus, you have two torus invariant divisors, there's just 6 of them. But S3 acts transitively on them, so you don't have prime divisors. And similarly, so there's nothing to blow up, there's no fixed points for this group. So this actually very powerful result. Okay. So and basically this is not criterion. I mean it's criterion in English language, but for example in Russian language criterion means if and only if. So it's this is not an if and only if statement. This is a sufficient condition. But in many cases it's actually if and only if. So for example, if the center of the automorphism group is trivial, this is if and only if. So you can say X is K-polystable if and only if these two conditions satisfy. But in general, there's some minor discrepancy, which I don't want to discuss, and so because of technical issues. Okay, anyway, good. So if you never saw this, and let's just consider some very explicit example. You take Delpezzo surface of degree 7, which is P2 blown up in 2 points, and you have two exceptional divisors. I already mentioned that these surfaces cannot be K-polystable because its automorphism group is not reductive. But it's using the previous criterions, we can show that easily that this is actually not even K semi-stable. Let's just do this. And this is illustration how to apply previous theorems. You blow up 2 points on P2. You have two exceptional curves. And then you take a third -1 curve on the surface. You take a strict transform of the line that pass through points P and Q. So this is the 3 -1 curves in S7. An anti-canonical divisor can be split, can be like this. So it's a sum of these 3 -1 curves with these coefficients. And if you remember, in the definition of beta invariant, we use this pseudo-effective threshold. So the first natural choice to compute beta invariance is not for exceptional divisors, but for some divisors which lives on your surface. So one can try to compute, in this case, beta invariance for L, E, E1, and E2. But if you remember this definition, that the larger pseudo-effective threshold, the smaller beta intuitively should be. Not always, but intuitively. So in this case, pseudo-effective threshold is 3. Yeah, you can subtract the L with multiplicity up to 3 to keep it pseudo-effective. So let's do this. Let's compute beta of L. So first of all, you look at this divisor, and the only interesting number is just this volume. And if this divisor is NEV, the volume is just the square, just volume of NEV divisor. Yeah. So and you just compute. This is this function 7 minus 2t. If t is larger than 1 and between 3, you have to use the risky decomposition of this divisor. So you have to split this divisor as like a NEV part and a negative part. Some bunch of curves which has a negative intersection form. And yes, wait, there's is it a question? Wait, Ilya, there is a question because I saw something in the chat. It's okay. Ilya,
I don't see any questions in
okay,
chat.
okay, fine. Because I thought, okay, fine. So let me consider. So this is the risky decomposition. You have negative part. So two curves, intersection form of them is negative definite, and this is a NEV divisor, and all these curves intersect NEV part by 0. This is called the risky decomposition. And then volume is just the volume of NEV part. So in this case, it's square. But this NEV part, you can see, just basically 3 minus t times full pullback of a line from P2. So this guy basically 3 minus t squared. Yeah, you see. And you can actually see in this example that the volume is actually a continuous function, and it's actually even differentiable. It's easy to see that you just take derivative of this, and t equal 1, it's actually coincide. Yeah. Okay, so you compute beta of L, and you see it's negative. So in particular, this is not K semi-stable. Okay. And in high dimensions, you can do this, but the amount of time is much larger. So basically, for example, for smooth Fano threefolds, you blow up some curve, you compute beta, it may take several hours. But still, it's very straightforward. Okay, so back to January 2020. In January 2020, this year, so basically a few months ago, Chinyang with Kent, I think with Chile, organized a workshop on K-stability in American Institute of Math in San Jose. It's a picture from here. And people on the first day of the workshop supposed to propose some problems. So I proposed the problem basically about Calabi problem for smooth Fano threefolds. So basically just to get explicit solution of this problem. So explicit answer, which smooth Fano threefolds are Kähler-Einstein and which are not. So in the same way as Tian theorem in 1990. So just explicit. These Fanos are Kähler-Einstein, which these are not, and something like this. Yeah. Okay, and several people joined this group, and then other people joined a little bit later. So we have a big team, like 9 people. So it's like a conference, small workshop. But anyway, so since then we basically been working on this problem, but a lot of things already been proved before. So there was a lot of results in this direction known before. So let me, yeah. But before mention them and before mention the methods, let me just say that so there are classical classification of smooth Fano threefolds by Iskovskih, Mori, and Mukai give us 105 families. And some of those families has moduli, some of those families do not have moduli, just maybe one threefold. Some of those families has like strange moduli consisting of 2 threefolds. Yeah, and a lot of results been already proved before. But let me just summarize. Let me in the next 3 slides, I put some table which summarize what is done. It contains everything. So what is done before us and what is done since January. So altogether, and in January 2020, around 52, 53 families among 105, the answer was known. So either some of them non-case stable or non-case semi-stable, or some of them case stable. So answer was known roughly for half of smooth Fano threefolds. Okay, so since then we basically dealt with roughly maybe 25 families, but our goal is not to give a complete solution of this problem, but to give a rough solution. A rough solution means that we want to know answer for generic element at first, if possible for every element in the family, but if it's hard, just for the general one. And so, for example, there's a famous book on Fano varieties called Fano Varieties by Iskovskih and Prokhorov. And in the end of this book, there's a table of smooth Fano threefolds. And this table has a lot of columns. One column, for example, rationality of smooth Fano threefolds. But even rationality problem, even now, despite the fact that people were working on this for 100 years already, so rationality problem for smooth Fano threefolds is not completely solved. But for the generic member of every family, we know the answer. But there are few families which we still don't know the answer for every element. So in some sense, case stability is the same. We don't want to answer completely for now, but just for generic elements. So let me give you the table. Okay, here is the table. This is Fano threefolds with Picard rank 1. Rho is a rank of Picard group. And you see that if you, so the star, so okay, we have this numbering of them. Numbering is from the book of Iskovskih and Prokhorov. Then there's a short description if it's short. For example, this 2 was, and this was long, so I didn't put them. Here it's a connected part of the automorphism group. So one can see which one has finite automorphism group and which families has non-infinite automorphism group. This column is K stability, K polystability, existence of Klerenstein metric, and this is K semi-stability. So star means generic. Yeah. So for example, in the first few cases, we know completely the answer for every element. But for example, even for complete intersection of 3 quadrics, as far as I know, that we only know answer for generic. Yeah, and there are 2 families, 1.8, 1.9, for which we don't know the answer for anything. We don't even know single example, and we don't know, I mean, conjecturally, they should be K-stable, but this is not yet. So this is 110. It's a famous Fano threefold, which was actually missed by Fano in his preliminary classification of Fano varieties, which sometimes it's called a V22. So it's a smooth Fano threefold of degree 22 of Picard rank 1. Yeah, and its automorphism group can vary like this. Generic one has trivial automorphism group. There's a special one which called Mukai-Omimura threefold whose automorphism group is PJ2, and there's one guy with unipotent automorphism group JA, and there's a one-dimensional family of Fano threefolds with automorphism group JM. So it's connected part. So a full automorphism group in this case slightly bigger. Here is J semi-direct product with Z4, and here JM semi-direct product with Z2. Okay. So in particular, in this case, we don't have Kellenstein metric. In this case, we do have. But all of them, for example, this GA guy, it's actually K-semi-stable because it's degenerates to this one. Okay, so this is a rank 1, almost done, except 2 families. And then we have this rank 2. So a lot of, in this table, a lot of varieties were known to be K-stable or not K-stable. So some results are new, some is known. I just basically give you just update. So we have, yeah, so, and then, but there are more with PK rank 2. This is just the first part of the table. Okay, and this is more, yeah. So we have more open cases, but it's basically a matter of time. So because each family takes quite a lot of time to deal with, so it's just a matter of time. Yeah. Okay, for example, this family is very similar to V22. And one can actually show that in some sense it should be, in some examples, for example, in GM, it's equivalently birational to V22 with a GM action. Yeah, okay. Then this is another one. So this is still rank 2. Yes, and so the numbers grows. So this numbers grows with a degree. So this is a high degree, and high degree basically, you see, many of them are unstable except like products. Yeah. And then rank 3, we still have few open cases, but a lot of cases are already done. And there's another one, rank 3, just the end of the tail. So also a lot of cases done. I will explain later the methods. And finally, the high rank. So in the high rank, starting from rank 5, with one exception, this is just products, P1 times Delpetsky surface. In this case, answer is known. And then we have quite explicit description, and with few exceptions, answer is known, but we still have. Yeah. So altogether, we have around 20 cases left to deal with, which we plan to deal before the end of summer. Okay, so the methods. So let's just take the first method, which I already mentioned. So if okay, if you have a smooth Fano threefold, if it's K-poly stable, that automorphism group was reductive. And 2 years ago, I and two my friends, Kostya Shramov from Moscow and Viktor Przhelkovsky from Moscow, we classify all smooth Fano threefolds with infinite automorphism group. And we describe connected components of automorphism group. In particular, this classification implies that 22 families has non-reductive automorphism group, and there are 4 special Fano threefolds such that a generic element of the family has a reductive automorphism group, but there are 4 explicit members with non-reductive automorphism group. So yeah, this immediately gives something. So, but yeah. Of course, there are a lot of toric examples. There are 18 toric Fano threefolds, and for toric variety, we have this theorem of Wang and Zhu, which says that X is Kellenstein if and only if barycenter of its polytope is 0. Yeah, and this condition, center being 0, it's purely combinatorial. So basically, right now you can go to this web page, www.grdb.co.uk. So it's called graded ring database, and you basically can just put all of these conditions there, and you can get the full list of toric Fano threefolds with this condition. Yeah, and you see. So this is purely combinatorial. In particular, we have 4 toric smooth Fano threefolds K-poly stable, and 13 smooth Fano threefolds which are not K-poly stable. So this, as you see, this is already give something. This, yeah, this gives like 35, even more, 35 plus this, 39 families which are not K-poly stable. So this is kind of first step, which was done long time ago. Yeah. Then another another kind of way to get a bunch of examples of unstable smooth Fano threefolds is to apply this theorem with beta divisor, with beta invariant, that beta of some prime divisor E is negative if it's K unstable. You can first apply it to divisors which actually lives in X, not over X. So you don't blow up anything. You just take X and you go through all surfaces in X. But of course, you don't need to go through all surfaces in X. You have to go through surfaces which basically generate the cone of effective divisors. And this was done by Kenta Fujita, who defined them such Fano threefolds divisorially K unstable. So Fano threefolds called divisorially K unstable if and only if, is by definition, if this beta invariant is negative on a surface in S. So you don't need to blow up, you just present the surface and you check. So Kenta described all of them, and there's actually quite a lot. There's 26 families such that all members of the family divisorially K unstable, and by some strange reason, maybe there is some, no, not strange, I think maybe one can prove it. So basically, this doesn't depend on deformation class. So if its condition is satisfied in one, for one threefold, it's satisfied for all threefolds in the family. Yeah, so it's exactly 26 families. Yeah, of course, these 26 families overlap a lot with previous families. So for example, for many of them, automorphism group is not reductive. So not for all, but for many. So, and actually every time when automorphism group is not reductive, it's divisorially K unstable. So this condition is actually better than automorphism group. Okay, but then we tried a lot to prove K instability by blowing up curves. So, for example, this result of Fujita give you computation of beta for all surfaces in X, but of course then you can blow up something and compute beta of exceptional divisors. So first case is you blow up some curves, and again you can start with curves which generate the Mori cone. We did this in many cases, and our initial expectation, was actually back to, we started this back in January in San Jose. Our initial expectation was that a lot of threefolds should be unstable by blowing up curves. If blow up curve, compute beta should be negative. And there was many families which looks intuitively absolutely unstable. But somehow we only got very few cases when beta is negative, very, very few. So one case is like this, and you can see how this, the next example show you how delicate this condition is. So for example, you take V5, it's called smooth Delpezza threefold of degree 5. So this is unique smooth Fano threefold such that anticanonical divisor is divisible by 2. And the Picard group is Z, and the generator of Picard group is cube of this divisor has degree 5. It's basically analog, three-dimensional analog of the Delpezza surface of degree 5. If you take my definition of Delpezza surface of degree 5 and there's a section of Grassmannian, you just need to raise dimension by 1. So this is section of Grassmannian. Yeah, it's also unique. So you take this guy and you take a line in it. So line is a curve which intersects anticanonical divisor by 2, because anticanonical divisor is, okay, should be V, this should be V. Anticanonical divisor is divisible by 2, so this is basically a line in the corresponding embedding. So there are two types of lines on V5. You can call them good lines and bad lines. For good lines, the normal bundle is O plus O of 2, and for O plus O, and for bad lines, very few of them, its normal bundle is O of -1 plus O of 1. And this is quasi-homogeneous threefold. So all bad lines, all lines with this normal bundle, they form a divisor which closed orbit, two-dimensional orbit of the action of automorphism group of V5. Automorphism of V5 is PGL2. So this all such lines form one divisor in V5, and all of them are the same. They can with up to the action of automorphism group. So this is a bad line. So you take this bad line and you blow it up. And then you can compute the automorphism group of you blow up. And automorphism group is actually a semi-direct product of GM and GA. So it's not reductive. So X is not KK polystable. So if I blow up other line with a normal bundle O plus O, automorphism group is going to be reductive. Yeah, it's going to be actually GM. So this is this automorphism group is larger and it's not reductive. So this is not K polystable, but actually it's even not K semi-stable because we can compute beta invariant for blow up of some curve in X. If this guy is actually divisorially K stable. So if you take all surfaces in X and compute beta, it's going to be positive. But there's one special curve there. You take F exceptional divisor, pi exceptional divisor, F the surface S is this exceptional divisor of this map, and one can show it's F2. So if L were a good line, this guy should be P1 cross P1, but now it's F2. And of course, F2 has a special section, yeah, -2 curve. You take this -2 curve and you compute by definition, you blow it up, and you compute by definition beta invariant of this exceptional surface. And it's negative. It's a long computation, but it's negative, yeah. And this is one of the very few cases when we get negative beta for blowing up of curves. Somehow we expected much more. Okay, good. So this is some examples how one can show K instability. Yeah, good. Then we go back to alpha invariant of Tian. I gave a definition in terms of blowups, but there's another definition in terms of divisors. It's a bit technical, but it's equivalent. But this definition is a bit better in some sense. I don't know. In some sense, it's maybe better. In some, yeah. So we fix a Fano variety, maybe singular, and we fix a reductive subgroup in automorphism group, and n is dimension, and we define this alpha g of x. It's quite technical. You take all anti-canonical linear system, and inside of them you go through all G-invariant linear subsystems here. You normalize them, like multiply them this d by 1 over m, and then you put some number epsilons here, and you take supremum by some epsilon that this guy has mild singularities as a log pair. Mild here means log canonical. It's very technical, but log canonical means that the corresponding log discrepancy A big or equal than 0. They're the same A's we defined a few slides upstairs here. So this is technical number, but in many cases it is computable. Okay, so there's a result which goes back to okay, now I feel bad. It goes back to a paper of Professor Yao Tian, but now it was reproved by Yuji Adaka and Sana, purely algebraic language, and then it was generalized by result of Datar and by result of Datar and Shikilhidi, and then after this by Liu and Zhu. This is very recent. Result of Liu and Zhu basically last year. So basically, if alpha invariant, G invariant alpha invariant, this guy bigger than n over n plus 1, then x is K polystable. So if x is smooth, basically this condition implies existence of Kerenstein metric, and this implies by the Yao-Tian-Donaldson conjecture K polystability. But in algebraic settings, it's much more subtle, because if your variety is singular, this condition by result of Adaka and Sana implies equivariant, G equivariant K polystability. And recent results will basically show that G equivariant k-poly stability is equivalent usual k-poly stability. Yeah, so we have this theorem. It's very powerful. It's very powerful. Yeah, but this theorem can be, in some special cases, can be a little bit improved. It's a little bit, but it's actually quite powerful also. So basically, if you assume here that X is smooth, and then if you assume that G is connected or finite, then even when you have equality here, it still implies k-poly stability. So if you, in this is a theorem of Kenta-Fujita, if you erase group here, if you just consider G is trivial group, now this is a paper by Fujita, which he proved a few years ago. But in equivariant settings, Kenta proved it as a part of our project. It's part of our project, but it's purely by Kenta. Kenta generalizes like this. And this is actually quite powerful. Let me show you some examples where this theorem is not applicable, but this is applicable somehow. So, okay, but this is supposed to be a joke. So this was alpha invariant of Tian. This is alpha invariant N Tian. So this is Professor Tian. This is me on a conference in Chitrara 2 years ago. Good. Okay, so example how to apply this theorem of Kenta. This is a very, okay, by the way, are there any questions so far? Okay, we have 8 minutes left, but maybe there are some questions. Maybe I'm going too fast. Ilya, are you still here?
Actually, I should tell you that the problem of Kähler answer metric was due to Kähler, not start from Calabi.
Oh,
You should read the first paper, Kähler geometry, defined by Kähler in 1933. He studied what Kähler answer metric is supposed to be in terms of complex motion pair equation. So when you say it's Calabi problem, it's a little bit unjust.
Kähler problem. Really. Oh, I didn't know. Thank you very much, Professor Yao. Thank you very much. I didn't know.
It's the very first paper, Kähler. You should read those old literature.
Okay, thank you. Thank you. Okay, let's apply previous theorem of Kenta. So you take P3 and you take a twisted cubic curve there, basically just curve given by t squared, t cubed, just twisted cubic curve. And you blow it up. Automorphism group of P1 is PGL2C, and basically automorphism of a pair P3 curve, which automorphism of P3 preserving the curve is just PGL2C. So the whole action of the group lifts to X. So this is the whole automorphism group. And then one can actually show that alpha G of X is 3/4. So basically there's only one choice of group here. If you take smaller subgroup, then alpha only drops. So without Kenta theorem, that's we cannot apply it. There are other methods how you can prove k-stability of this, but at least this, and the proof that alpha G of X is 3/4, it's actually very nice. It's use some classical birational involution, which basically only undefined along the twisted cubic curves, some mega classical, which goes back to the 19th century. Okay, this is one example. Another example is more sophisticated, but we try to deal with this case using other methods, and we failed. So you take a quartic surface in P3, given very strange equation, but I will explain what this strange equation means. First of all, it means that the surface is singular in the point 0, 0, 0, 1, and singularity is ordinary node. And another condition why it's so special, that it's actually acted by the group S4. It has the S4 symmetry. Then you blow up P3 in this singular point, this surface. So preimage of this surface S4, it becomes actually smooth once you blow up. So it becomes smooth K3 surface. And the action of the group S4 lifts to blow up. And this is traditionally called V7. V7 is a blow up of P3. So this V7 is unstable, very unstable Fano threefold. But now we take a double cover of this unstable threefold. branched in this quartic surface. And you a little bit extend the group. You take the group action of the group S4 leads to X, but you also have Galois involution of this double cover, so which is direct, give you direct product. So you take this group, and you can show that alpha invariant of this is 3/4. And you can show that in the whole family, this is a family number 2,8, equivariant alpha invariant cannot be larger than 3/4. Yeah, but it can be 3/4. It's not hard, but it's also not obvious how to prove this. So this is also K-polystable. And actually, in this case, it's K-stable because automorphism group is fine in this case. Okay, another method. Another method is a generalization of Rui-Dervan theorem, but I didn't put a Rui-Dervan theorem here. I put our generalization, but I'll show how to get the original theorem. So this result, it's actually a little bit reminds you that we got this result because we wanted originally to prove K-polystability of this X in this example using different methods. So, but it didn't work. We tried, but it didn't work. So, namely, let's consider new settings. You have Y, it's a Fano variety with KLT singularities. And then you take some divisor, some surface, and okay, like some effective reduced divisor in Y. You assume it's proportional to minus K with some rational number. And then you also assume that there exists a cyclic cover of order M which branched along this B. Okay, and then you are, in most of cases, X is not Fano, but suppose it is. So suppose that X is also Fano, also with KLT singularities. So this line imposes condition both on B, on M, and also on singularities of B. So B cannot be very singular, and this B and M related, yeah. B cannot be very big, yeah. And suppose one of the two conditions satisfied. Either this pair, Y and B branch divisors, log canonical, and delta of Y is not very small. It's like this. So it's, yeah. So if delta less than 1, it means that Y is K-unstable, not K-semi-stable. But so delta in this case can be less than 1, but not much. This first condition. Or if this condition is not satisfied, we can a little bit weaken this. So we assume that delta is actually equal with M minus 1B. This pair is log canonical, but we also assume that this ratio A of E, where A is this log discrepancy and S is a number defined long time ago, is actually strictly bigger than M minus 1B for every prime divisor such that log discrepancy of this log pair is 0. So basically, this log pair is log canonical means that all log discrepancy of this log pair, if you blow up all log discrepancies, are bigger or equal than 0. So if one of them is 0, then we wanted to satisfy one exceptional divisor give you 0 log discrepancy. We want also this. So if all of this satisfy, then X is K-stable. So it's basically just straightforward generalization of Dervan theorem. In Dervan theorem, Y is smooth, X is smooth, so all of this condition automatically satisfied. So this disappear, and delta is 1. Oh, not 1. Delta is bigger or equal than 1. Delta is bigger or equal than 1. Yeah. So, but this is so our goal was to apply the theorem to this threefold X, but it actually didn't work. So this is why we got this example. But this theorem can be applied in few cases, but most of them already covered by Dervan theorem. So for example, one theorem which is not covered by Dervan theorem, it's a smooth sextic hypersurface in P11123. This is Fano threefold Picard group Z and degree 8. So it immediately gives you K-stable, but alternative proof K-stability of this is given in the very recent paper by Jikwan Joan and Hamid Ahmadinejad using completely different method. And this is two examples basically from Dervan paper. So if you have, for example, smooth Fano threefold number 1,5. In Iskovskih Prokhorov book, this family splits into two. Generic member is a complete intersection in this Grassmannian of in the Plücker embedding with some quadric and with a linear subspace. But there's a degenerate member, which is double cover of the threefold V5 we discussed before. So this guy is the generation of this. And to the second case, you immediately can apply Dervan theorem. So it's case stable. It's actually surprisingly that, for example, this first family, generic element of the first family is known to be non-rational. But this subfamily is the generation of this one. So, for example, non-rationality of this is not known. I mean, it should be not very hard to prove, but it's not known. Okay, and for example, in another case, you have smooth Fano threefold number 226. So generic member is a divisor in P2 cross P2 of degree 2,2, but there's a degeneration of this. Is basically it's a double cover of divisor in P2 times P2 of degree 1,1. Yeah, so in this case, it's Dervan theorem immediately implies it's case stable. Okay, but finally, I want to, okay, I'm a little bit over time, but let me mention final result, also relatively recent results by Bloom, Liu, and Chinyan-Xiu, so which says that case stability and case semi-stability are open in families. This is very powerful. So for example, if you go back on the previous slides, this example implies that generic element in each family of these two families are case stable because it's open condition, open in Zariski topology. And here I just put one very strange examples. So basically you take intersection of two quadrics in P5, which is known as a Fano threefold V4, and you take a conic on it. It's very explicit conic. You blow it up, and this is Fano threefold number 216. But in this case, this is just an example with the action of the group A5. Very small group, but one can show that this is probably one of the largest group which can act on X. And alpha invariant of X without group action is actually small. It's 1/2. But if you take into account this group, it actually jumps to 3/4. So it's case stable by this Kenta-Fujita theorem. So using the openness results, we get the general smooth Fano threefold is case stable is in this family. Yeah. Okay. So let me stop here. So sorry for if I a little bit take over time. Okay. Yeah. Let me stop. Yeah.
Well, I guess we'll thank the speaker. I don't know how we're gonna do it, but
there's an option in. There's an option in to click on
reactions.
Reactions, okay. Okay, so we have any questions for Ivan?
Can I ask questions?
Absolutely, yeah.
Can you just roll back of your slides to this number 1.5 Fano threefold?
Yeah, this one, yeah.
Is this degree 10 Fano threefold?
Yeah, absolutely, correct.
So can you say it again? What about some case stability result for the first one? I mean, this.
Okay, put it this way: this degenerate case, double cover of V5, ramified into anti-canonical surface. It's immediately case stable by Dervan. Just, yeah, but for this one, you can say since this explicit degeneration that X one can take. You can take guys in the generic member X and you degenerate it to the double cover. It's very explicit degenerations. So using openness, you can conclude, and since automorphism group of all of them is finite, you can conclude that generic element in the family is case stable. Of course, of course, it's expected that all of them are case stable.
I see.
And as far as I understand, Hamid Ahmadinejad and Zhikwan Juan, I think they're probably working on this family to prove that all of them is case stable. As far as I don't know, Hamid, are you here?
Yes,
Okay.
I'm here.
Yeah. So did you prove this already? That all of them are k-stable?
We started from V22, so yeah, soon.
Ah, okay.
We're
Okay.
going back.
Anyway.
Yeah.
Okay. Anyway,
Soon.
so all of them conjecturally in this family should be k-stable. All of
Okay.
them.
Thank you.
Okay. Oh, Jikwan is also here, and Yuchen is here. Oh. Okay. So,
more questions, more questions, more questions?
Or comments, maybe comments?
Or comments? Okay, then we'll thank the speaker again, and thanks to everybody who was participating.